maybe let me say, well, I mean, hopefully this will be fun for you guys. It'll be fun for me. It could have been more fun to actually visit in person. Sorry, I'm kind of, you know, sort of, well, yeah. So yeah, I'm supposed to talk about localization for affine W algebras. Let me make this slightly larger. Yeah. So and sort of so here's kind of the rough structure of what I'm going to tell you about today. So what's kind of the plan? So for the first half, I just want to recall some salient features from the representation theory of W algebras. And so then, these are due to many mathematicians and physicists over a long period of time. And then kind of the idea is that we'll see some patterns that kind of, and so we'll see some patterns and we'll see some sort of character formulas and whatever that kind of all have this Kaj-John-Lustig style flavor. And so then the basic idea is that, say, normally, how do you prove Kaj-John-Lustig type character formulas? You find some equivalent realization is perverse sheaves somewhere. And so let me just quickly say, so some of the relevant names for this first half, and there's many, many more that I'm omitting, and with all apologies to the relevant people. So this is just some of the names. So Katz, Feigin, Fuchs, Frenkel, Felder, Wakimoto, Arakawa. Okay, and then, okay, so in some sense, kind of, well, the first half is going to be to sort of explain like what it is, like what is the point of trying to develop a localization theorem for W algebras? And it's kind of like, well, it's kind of, the representation theory has exactly that kind of flavor of like, it's something which is exactly tractable in the ways that, the things you normally do by perverse sheaf games in simple enough perverse sheaves and simple enough spaces. Like it kind of fits into that flavor of thing. So in the second half, I'll then sort of describe sort of the corresponding localization theorems. So basically, what's a way to kind of get all the answers we see in the first half using kind of geometric techniques. Okay, and sort of this is the second half is based on some I feel like the word classical is like extremely overused, but let me just have fun with it. So actually, it's from a little bit ago, but just some older work with uh, Professor Sam Raskin. Yeah, great. Okay, so are there any maybe questions before we get started?
So far, so good.
Okay, so far so good. Yeah, great. Okay. So let's actually discuss sort of rep theory of W algebras. And so I think maybe, well, what's the best way to say this? So the same way that when you want to learn representation theory of semi-simple Lie algebras, kind of, there's some general formalism of roots and all that kind of stuff. And basically it's some way to kind of extend what your brain knows happens for SL2 to higher rank things. And there's an absolutely similar thing here. And so basically, I think I want to start with just the Virasoro algebra, and then we'll worry about sort of higher rank groups. Okay, so what's the idea? So let me recall for you sort of, so maybe let me start with sort of just Virasoro. So okay, so what is the Witt this is the W algebra for SL2. I think this was something you already covered in this seminar. Um, yeah. So let me recall how this works. So what's the Witt algebra? So that's kind of it's the following thing. So it's just you take uh, vector fields on a formal disk with the usual Lie bracket. And let me recall for you a convenient basis for this algebra, topological basis or whatever. Oh, yeah, by the way, so yeah, most technical things about like topological bases or completions or whatever, like I'm not, I will likely, I'll either intentionally or accidentally not say them. So, if you have questions about the things you can ask, but yeah, it's maybe not so important to follow the doc. Okay, so this is a nice basis given by the following elements. So the basic idea is kind of say if you want a triangular decomposition or something, typically it's you want to grade your Lie algebra by the integers, take some positive part, negative part, whatever. So, grading by integers, that's some sort of GM action. So where's the GM in this game? It's just, we're doing vector fields on a disk and you can just rotate the disk. Okay. So um, so let's introduce explicitly the following vector field. So it's just you just take a monomial in T times the standard vector field d by dt. And so here's kind of so how do they bracket with each other? So the formula is if you take Lm and Ln, you get the following thing. So everything here is graded, so you should get something, some multiple of the m plus n one. And which one do you get? You get m minus n times. And I mean, well, like I promise you, there's nothing mysterious going on here. It's just the usual formula for Lie brackets, right? So let me just remind you, I take this and this, like what do I get? I get like basically f of t, g dot of t minus f dot of t, g of t times d by dt. Okay, and you plug in just these monomials and you get what you want. Okay, so so that's the Witt algebra. And kind of so what's Virasoro? So Virasoro is kind of basically the idea is that like there's many, many, many vector spaces which come up that kind of seem like they should have an action by the Witt algebra. Let me recall. So the Witt algebra, the whole point is that it's so vector fields and something that's the algebra of automorphisms of that thing. So basically, whenever you write down something like completely local around some function, around some point in a Riemann surface, you're going to get some action of like automorphisms of the formal disk around that, or automorphisms of the formal puncture disk around it, roughly speaking. And the idea is that sort of in many times, if you actually do it carefully, you don't literally get actions of that group or the corresponding Lie algebra. You get an action of the central extension. Yeah, it's kind of related to this business of kind of like there's sort of phase ambiguities roughly when you want to talk about like a single state in quantum mechanics or something. You can't really see the e to the I theta if you're working. Yeah. Okay, so anyway, so what's Virasoro? So Virasoro is the good news is kind of there's not so many central extensions of the Witt algebra. There's basically only one of them. Oops, that's definitely not what I mean. Sorry, so we have this. So there's going to be just one central extension around, and let me recall for you what the modified Lie bracket is. So here C is central. So C with anything is equal to 0. And 2, so the interesting thing is what's this kind of modified bracket? So it's when I take the bracket of 2 of my previous vector fields, I should be getting sort of the term I had before plus a new term. And let me first write down what that term is. It's a very beautiful looking cocycle, and then I'll say a little bit about how you can read it. So it's kind of this extra term only turns on when the m and n have opposite charges. And it's okay, so now we're going to get this central term. And what's the coefficient in front of it? So the idea is that it grows as the m grows. And let me tell you exactly how it grows. So we take the following expression. So I take m times m plus 1 times m minus 1. And there's some convention or whatever where you divide this by 12. And there's good reasons for that convention. But if you haven't seen this before, just think of it as a convention. And so maybe just the basic remark to make about this is say, if you're reading this formula, like, okay, so there's some sort of 12 there. Okay. How do you think about this numerator? So the way you think about the numerator is the following thing. So it's kind of, again, so width, that's something like vector fields on, say, some formal punctured disk. And so then the idea is that sort of suppose you embed, just think of this as like the formal punctured disk around t equals 0. And so then certainly inside of all of these interesting, many vector fields on this little punctured disk, but inside of there, you also just have sort of vector fields on, say, just all of P1. So there's t equals 0. Vector fields on P1, we know what they are. That's just SL2. And famously, SL2, or sort of finite dimensional semi-simple algebras, do not have central extensions, non-trivial central extensions. So the statement is that it's kind of, this is some sort of three-dimensional subalgebra of this one. It's the subalgebra you would think, which is, it's the span of L0, L minus 1, and L1. And so kind of the rough, I mean, of course, there's many ways to normalize a cocycle, and you can change it by a co-boundary. But roughly what's going on in this cocycle is it's kind of recording the fact that like whatever you're doing should be trivializable on global vector fields, and why not just make it trivial on global vector fields? Because namely, it's kind of, again, this will literally vanish when m is equal to 1, 0, or minus 1. Yeah. Okay. Are there any questions? Okay. Great. So, anyways, okay. So the rough idea is you want to study or classify, say representations of Virasoro. And so I think maybe let's just start extremely naively. So it's, suppose you've never thought about this problem before. Okay, so like the rough idea is you want to think that Virasoro with its triangular decomposition is something like a semi-simple Lie algebra with its triangular decomposition. And so I think maybe the first thing you might try is like, you can ask sort of, okay, so let's try to classify the finite dimensional representations first, and then go to some sort of category O. So let's just try to do that and see what happens. And the one slightly disconcerting thing, if you've not done this before, you've seen someone do it for you, it's kind of that this is like a big algebra, right? It's an infinite dimensional algebra. And so a priori, that might make you suspect that finite dimensional representations aren't really a sensible thing to be looking at. And indeed, that's the case, but let's just do it. So, okay, so here's kind of the first lemma. So the claim is that it's sort of any finite dimensional Vir module is a direct sum of copies of the trivial representation. And so I will certainly not be proving like hardly anything for you in this talk, but this thing actually, it's kind of, I think, let's just kind of get our hands slightly dirty and just see what's going on for a couple times, and then we'll sort of just start stating things. Okay, so what's the idea for this? So what's the proof? Okay, so how do you normally classify, say, finite dimensional representations of something? You kind of, well, you want to play with sort of highest weight vectors in them. Okay, so let's just say, so suppose if V was a finite dimensional irrep, So consider just the action of in fact, by the way, whenever I say modules, they're always smooth. So in other words, kind of this is some topological Lie algebra, and you just want any element is sort of annihilated by all the sufficiently high modes. It's like L a trillion and above or something for the appropriate value of 1 trillion. Um, so consider just the action of first Vir 0. In fact, let me call this M. So it's maybe just already a V in the game. Um, so this is kind of the span of L1, L2, L3, L4. Okay, so this is what's even the best way to say this? Um, yeah, okay, so well, yeah, I'll just sketch it. So the revenue, so this is some sort of pro-solvable thing. Um, so it's basically one, it's pro-solvable, and two, the other observation is that when you just take something like L minus N, Ln, and their commutator. So basically, we said this for n equals 1 before, but it's true for any of these that kind of these generate for you a copy of SL2. So the idea is that this statement will tell you that each of these LIs for I positive is going to be acting locally nilpotently, actually nilpotently, since it's a finite dimensional thing. That plus pro-solvability. So this implies for you that basically there'll exist some M in M, so which is kind of killed by V greater than 0. Great. And then now, so then the next thing is kind of now let's consider also the action of Vir 0 on sort of these invariants. And so this is explicitly, this is the span of two guys. This is L0 and the central element. So let me recall. So L0 is just the Euler vector field. Okay, so the claim is that so C is going to act by a scalar, which sort of confusingly people normally just write as C again. Okay, let me just do some horrible notation. So I'm just going to write a math frac C just to make it clear it's just now some number. That's just by Schur's lemma. And then, so L0 is going to act sort of, in fact, semi-simply. Again, just from the SL2. So in particular, so the upshot is that this M is going to be generated by a highest weight vector. So it's going to be there's some M in it such that sort of Li times M equals 0 for I greater than 0. L0 times it, L0 is going to scale it. So this is some other parameter, some other complex number. And then our central element is going to be acting by some scalar. Not just on this highest weight line, but on the whole module. Okay, so already we've seen that basically, so there's going to be, well, wait, essentially we're talking about finite dimensional representations, but what we've now seen is that for something like a Verma module, there's going to be two parameters for the highest weight. So there's how L0 acts on the highest weight line and then the central element. Okay, so now how do we sort of proceed from here? So it's the following nice thing. So okay, so sort of for M to be finite dimensional, sort of we would need in particular that just acting by each of these, SL2s. Um, so just acting by each one of those SL2s on the highest weight line, this should be finite dimensional with a uniform bound on the dimension, so independent of n. Um, but so let's just kind of figure out what's going on for that. So the basic idea is that, okay, so let's just see what's going on. So if I literally take, let's say, the commutator of Ln and L minus n, I get the following element. So I get sort of, so this is kind of the important term. So it's I get 2n times L0, and then there's kind of this extra term, which will be here, and we need to deal with it, but you can kind of ignore it. Okay, so okay, so this is going to be some scalar multiple of the usual h in our SL2 triple. So let's call this thing h prime. So our actual h, what should it be? What we need to do is kind of so we know that h acting on, say, Ln should be 2 times Ln. And our h prime acting on Ln, what's kind of coming from this thing, it's I get 2n squared. So the upshot is, so the point is that, so therefore h is equal to h prime divided by n squared. And so the point is that it's simply go sort of this h acts on sort of m, the highest weight vector, by the following expression. So it's I get something like, and it's okay. So 2n delta plus n times n plus 1 times n minus 1 over 12 times this central thing, and then the whole thing divided by n squared. Okay, so this is kind of something like 2 delta over n plus n plus 1, n minus 1, 12n times c. Okay, so now, so the rough idea is that now, so just basically the stupidest thing to say is that all of these need to have some uniform bound on how big they are. Yeah, like these should all be a bunch of positive integers, and they can't be going off to infinity. They can't be like 5, 13, 28. Like there needs to be a uniform bound, or else kind of that already shows you the representation is infinite dimensional. And now the basic point is just that sort of as n goes to infinity, sort of the dominant term here is, I mean, you basically just get something like the central charge, maybe times n over 12, something like that. So that tells you that the central charge would need to be 0. But then on the other hand, you would need that sort of 2 delta over n is a wait, have I done this wrong? Yeah, this is fine. So this needs to be a positive integer. So it's telling you that 2 times delta is in n times the positive integers for all n sufficiently large. And that also tells you that then delta has to be 0. And so it's telling you that sort of our m just was the trivial module. And then you can play some game with extensions to kind of, I mean, it's not hard, just for each SL2 separately, you would know any extension of this thing would be trivial. So the whole thing acts trivially. Okay, anyway, so the upshot is just that kind of maybe the first thing you would try to do, which is looking for finite dimensional representations, is not really any, there's just the trivial module. Okay. Are there questions about this? Okay, so funnily enough, just playing with the trivial module will actually kind of give us a pretty good feel for hmm, kind of what the flavor, what the structure of representation theory of W-algebras kind of looks like. Um, so the idea is that so let's just kind of state more formally some of the things that came up in this proof. So here's kind of a definition. So for kind of two scalars, let's say C delta and C, kind of the Verma module. So basically we can make sort of the freest possible module generated by highest weight vector with sort of these eigenvalues of kind of our torus on the highest weight line. So namely it's the so like the diagram is kind of you have Vir greater than or equal to 0 includes into Vir and kind of projects onto Vir 0. And again, explicitly, this is just the span of our central element in L0. This is those two guys plus all the higher things, and so some sort of parabolic. Okay, so then you can kind of define it in the exact same way. So you can just do the parabolic induction from Vir 0 to Vir of just sort of say a line which kind of is acted on by Vir 0 by kind of these two scalars. Okay. Okay. And basically, so to get some flavor for the size of this thing, it's basically looks like sort of say, formally it has some PBW filtration. I'm going to tell you the associated graded, but the basic picture of it is kind of you have sort of you're generating state, then you can sort of take, say, like just literal derivatives of it. But then kind of now you also have like in okay, so the rough idea is kind of so it has some sort of weight space decomposition with respect to L0. So this one's kind of L0 is acting by just the conformal dimension we specified. Then here it's kind of going up by 1. Here it's going up by 2, etc. Okay. So the general thing it looks like polynomials in L minus 1, L minus 2, etc., acting on the highest weight line. Okay. So typically you can talk about the character and it's typically talk about the character of this thing. And you get kind of so you have the highest weight line, and then you kind of have sort of from say powers of L minus 1, you get a 1 minus Q. From powers of L minus 2, you get a 1 minus Q squared, etc. So you get the following expression. Okay. So I mean, again, this should remind you of the usual things if you take some e to the lambda over the product of the negative roots or something. Okay, great. So yeah. So okay, so maybe the thing I want to say is that sort of so far what we said was that we had a surjection from this one Verma module to the trivial module. And that target was like the unique finite dimensional irreducible representation. And you can ask kind of like, how do you extend this to a resolution, for example? Like, how do you describe the kernel? How do you describe the relations between the relations, etc. Okay. And so kind of so the rough idea is the following. So so well, like explicitly for this one choice, we kind of can just eyeball, So like it's I should do that. I no longer remember how to do that. But anyway, so the basic point is that it's so here's some explicit elements in the kernel. So the kernel basically corresponds to the augmentation ideal. Of so just these negative modes. Okay. Um, and so in particular, sort of two elements in it. So okay, so the rough statement is that it's what would it mean for this to be generated by one? Well, let me try to say slightly better. So okay, so the idea is that it's so we literally have our actual state 0, 0. And so uh hmm, so the thing I'm trying to say is that kind of so like literally anything that has strictly higher energy is in the kernel. So let's just try to write down some particularly nice low-lying things that will hopefully generate the whole thing. Okay, so certainly just acting by a single monomial seems pretty good. Let's try L minus one and L minus two. So if we just try L minus one by itself, it can't be enough because sort of uh yeah. So well, let me try to justify this. So the claim is that it's so the first observation is that uh, basically Vir less than 0 is just generated by L minus 1 and L minus 2. So it couldn't be just generated by one of them, because then you have one-dimensional algebra, but if you just put both of them, then you're good. Um, and so that tells you that this augmentation uh, is kind of generated by just these two things. And the other thing which one can check is that sort of both of these two vectors are again highest weight vectors. Um, so let me maybe yeah, let me do the check for you for L minus 2. And kind of well, so the what on earth am I trying to say? So for L minus 2, you kind of need to check the following thing. So it's you need to check that sort of L1 times this should be 0. And L2 times it should be 0. Okay, and so I mean, how do you ever do these types of calculations? You just, you do commutators, right? So let me maybe just okay, let's do it. Um, so let's say this first one. So what would it be? It's going to be equal to well, it's going to be L minus 2 L1 times that, uh, which is that's kind of 0 by definition. Then we pick up this commutator term. And what is this? So this is kind of, yeah, actually, now I'm kind of confusing myself. Sorry, excuse me. I should be saying this. So maybe this one, no, sorry. Sorry, I'm sorry. Well, sorry, okay, I've written something slightly kind of wrong. But anyways, the upshot is that it's you. you do get two things. Yeah, in fact, sorry, let me try to say this slightly better. Actually, so maybe a safer thing to say is, excuse me, sorry. So it's yeah, so it's L minus one times this. That will be a highest weight vector. And then so maybe the statement should have been that this thing will be highest weight modulo sort of the submodule generated by L minus one, and you can explicitly lift it. So anyway, but the upshot is that you get the following thing. So we had this trivial module, and now we kind of get, so we had M00, it's projecting onto it. And now kind of we get two things giving us the kernel. So it's kind of, we're still at central charge 0, but now conformal dimension 1, central charge 0, conformal dimension 2. Okay. And so now let me tell you how this continues. Okay. So the claim is that it's sort of the next term, it will again be the sum of two Verma modules. But now the conformal dimensions will be 5 and 7. And then there's something like this going forever. So it's always just a direct sum of two Verma modules. So this is some sort of BGG resolution that, as far as I know, was found by Feigin and Fuchs. Maybe possibly I should mention Wallach and Rocha Caridi. Okay, great. So maybe the upshot is just that the way you can visualize this sequence of maps between Verma modules is kind of like you have something at the top. There was two things immediately below it. So those were these things with conformal dimensions 0 and 1. There's two things immediately below that. That's the things with dimensions 5 and 7. And you kind of go down forever. Okay, so this is kind of the picture of the Verma embeddings. Okay, and so actually, Miller, do we take a break halfway through, or what exactly is the plan?
At 3:55, we can take like a 5-minute break.
Great. Okay, cool. Yeah, so let me maybe sort of say then sort of how this picture, well, actually, before I should say how this picture generalizes, let me quickly just mention something which is kind of cool. So these numbers which are showing up here, so 0, 1, 2, 5, 7, etc. Actually, maybe let me sort of color them slightly differently. So yeah, what am I trying to say? So these actually, so wait, does anyone recognize these numbers? I'm kind of curious. Well, sorry, I mean you probably recognize the literal numbers, but the point is these are kind of they're called the pentagonal numbers. And the point is that sort of what's going on here is that when you take the Euler characteristic, you get the following identity, which is that if you write Pn for the number of partitions of n, what you get is that this is equal to Pn minus 1 plus Pn minus 2 minus Pn minus 5 minus Pn minus 7, etc. So the point is like it's the same way that normally these denominator identities for Lie algebras are storing very nice sort of algebra combinatorial identities. So it's kind of
Can I ask you a potentially homological algebra question?
Yes.
okay.
So I have this exact sequence down here, and I have this as a complex, and this is a complex. And then I think there's maybe like homological algebra sequence that
Ah.
allows me to like,
Okay, perfect. Great. Okay, we're good. Yeah. So I do not think that was a question for us. I apologize if it was. Okay, so the upshot is that this is some classical recurrence for the number of partitions of a number n, going back to Euler. So the funny thing is both Euler characteristics and this partition thing both go back to Euler. Great mathematician. Okay. And yeah, fun exercise is going to deduce this from having this resolution. Okay, so yeah, so maybe let me actually quickly plug in my thing. So actually, I'll go off screen for a second, but yeah. So yeah, so kind of. Wait. So actually, if I move slightly, will you still be able to hear me?
So we can.
Hopefully, yes. Okay, great. So yeah. Okay, sorry. So the point is that for literally just the trivial module, we found this sequence of Verma embeddings. And the point is that it's kind of, this is the picture which will generalize well, like not asking for finite dimensional representations, but asking for these types of embedding diagrams for Verma modules. Okay. So the point is that more generally, sort of Katz, Feigin, and Fuchs classified all homomorphisms between Verma modules and they found the following sort of very beautiful patterns. So let me remind you, this was the picture for this was literally, this was M00 up top, and this whole particular thing was happening at central charge equals 0. Okay. So let me tell you the kind of patterns they found. So kind of maybe the most generic behavior you'd expect is kind of sort of, the same way that sort of if you take a random highest weight for just category O for say semi-simple algebra, already the Verma module is irreducible, it doesn't talk to anybody. So generically, kind of you just get a single point. So most Vermas are just irreducible and they receive no maps and give no maps to any other Verma modules. Then you kind of get some sort of subgeneric behavior, which is kind of, it'll look like sort of a regular block for just finite dimensional SL2. So you get kind of two Vermas that kind of map to each other. But you guys can still hear me okay, is that correct?
That's right.
Great, okay, perfect, yeah, good. So, and then now kind of, so the interesting thing is that then past these kind of cases, you get sort of, there's a dichotomy. So let me sort of draw it for you. So the statement is that sort of at one type of level, you can get sort of these things which kind of look like that same pattern we saw before. Or kind of a slightly more singular version of it. And sort of these types of things occur when the central charge is in basically, it's like something like 1 minus a rational number. Okay. And then the other type of thing which can happen is you get what kind of look like the flips of these diagrams. So kind of so basically now instead of there being sort of a top Verma module and then sort of a syzygy going down forever, now there's kind of maybe sort of a simple Verma, and it kind of embeds into another, etc. And then you also kind of get the slightly less singular version of that same picture. Okay, and where do these things happen? They occur in sort of C in 25 plus a rational number. Okay. And so kind of there's some very nice kind of thing here where so the thing you're supposed to notice is that kind of these two types of pictures are kind of they kind of look like the flips of each other. Like if you just reversed all the arrows. And kind of that's yeah. So well, there's a whole fun story there. But in fact it's a fun story that you guys know all the words to appreciate. So so the idea is that kind of this kind of comes from sort of there's some sort of the point is this, there's some sort of BRST functor from Virasoro at central charge 26 effect. And kind of these Verma embeddings are kind of some consequence of sort of so basically the duality of Verma embeddings that's some artifact of kind of sort of basically it comes from sort of semi-infinite homological duality. So maybe just to put it even more plainly. So the point is that sort of so for maybe so basically for a semi-simple Lie algebra, the corresponding sort of homological duality tells you that if you take the Verma module with highest weight lambda, basically the substitution kind of when you send lambda to lambda minus 2 rho, that kind of flips all the arrows of Verma embedding. So it kind of looks like some long intertwining operator. So this kind of flips Verma embeddings. And so for people who like, well, if you want to understand what on earth I'm actually trying to say, I'm trying to say the following functors that you take a module and you send it to RHOM from it into just enveloping algebra, you know, maybe if there's some shift and twist. And that thing kind of that specializes to this. And similarly, so for Virasoro, you get the following kind of things. It's called Feigin Fuchs duality. It's kind of you send M C delta to M 26 minus C 1 minus delta. Okay. So anyway, so there's some details here which we're not going to cover, but the basic upshot is kind of so when they just directly studied sort of these kind of highest weight representations of Virasoro, they kind of saw, okay, there's some sort of pictures which look like the usual pictures you see when you're doing representations of, say, you know, so this is kind of, you know, so to speak, this is something like the case of a torus. This is the case of finite dimensional SL2. And then sort of these types of pictures. So the point is kind of what do they look like? Well, the statement is these kind of look like so let me actually say it precisely. So so sort of what should this diagram remind you of? So the point is that it's what this looks like is sort of if you say talk about Verma embeddings for just finite dimensional SL3, you get the following picture. It's you know, it's a dihedral group with 6 elements. If you do SP4, you get just a slightly bigger one. There's kind of some extra layer in the middle. And similarly, if you do G2, you get sort of again just kind of The point is it kind of the point is it's kind of basically just dihedral groups give you these types of patterns where kind of the sort of the length of the middle bit kind of grows as your braid relation kind of gets a little bit funnier. So this is like MST is 3, MST is 4, MST 6. Sorry, it's good. This is like the I'm trying to say sort of I'm saying that the braid relation in the bottom. So it's whether you're Dinkin diagram, you have like single bond, double bond, triple bond. Okay, so the basic idea is that so then you can ask the following question, sort of, why does Virasoro seem to behave like some sort of infinite dihedral group? And maybe a related question is sort of so actually maybe they'll sort of say for you. So there were some physicists in the 90s who looked at these analogous questions for higher rank W-algebras, and they found similar pictures. So in fact, maybe let me just sort of say similar question for sort of higher rank W-algebras. And actually, let's see how we're doing on time. Yeah, so, well, maybe I'll state slightly more formally what these character formulas or whatever look like after the break, and then I'll sort of explain the localization terms, like what they have to do with these pictures. Okay, yeah, maybe we'll break for this.
Great. Yeah, let's return at 1 past the hour.
Yeah, great, yeah.
Can I ask
Yep.
can you comment about why 26 appears?
Yes.
Why does it appear? Like why 26?
Oh, I mean, so I think the statement is like, well, okay, so first let me say it in, what's the best way to say this? Okay, so, okay, let me say it in two ways. So the kind of way one is basically that, so, okay, the general mechanism here is that when you want to talk about semi-infinite cohomology, right, there's this Tate extension of any infinite dimensional Lie algebra, and the Tate extension is the one where you can actually define semi-infinite cohomology. Yeah, there's some anomaly, and so this. I mean, the statement is just that. So just if you didn't use this specific normalization or something, you would notice there's supposed to be one particular level where you have this thing, and there should be some duality around that level. Now, so now a reasonable question is sort of, but like, why, when this normalizations or why did it actually come out to this very nice integer? And maybe that's what you're asking? Yeah. So, I mean, there's different ways to say it. I mean, I guess maybe the most famous instance of where this kind of comes from is it's related to this business of like, I guess when you do like, was it like bosonic string theory? You kind of, well, I mean, basically it's kind of, you know, the rough picture is like, so you have sort of, you're mapping your Riemann surface into just some flat space of some dimension. And the point is that it's like, basically for each coordinate direction in your target, that adds 1 to your central charge. And basically the only, like basically, well, the same is basically there's some, basically the fact that it comes out to be this exact integer 26 is related to the fact that like, whatever, bosonic string theory is really, it's like, like there's some anomaly which you need to cancel, and that only happens if your target is 26 dimensional. So maybe this was not an answer, but just maybe the point is that it's like, The fact that it
Maybe
goes out as an integer in this normalization is, well, please, maybe someone,
maybe I can answer it in a different way.
please.
So this 12 in the denominator of a central extension and
Yes.
both and 26 that Nikolai was talking about,
Yes.
they are not accidental. They are actually coming from the Ramanujan and eta function, where you also have this 26 in there as a prefactor. And this is not quite completely accidental. Well, it's not accidental because, first of all, if you look at the character formula, it does look like some, I don't know, number theory. So it is one of those classic functions. And
Yes.
I believe that actually there is a proof of one of the reciprocity laws by using Virasoro, by De Concini and Katz, I believe.
Yeah.
So there is some number theory hidden in it, but
yes.
I don't know if it's whether it's related to what you say, this string theoretic anomaly.
Yeah, no,
I think it is, but I'm not. I don't remember how exactly is it related to.
sure. Yes. Yeah, and in fact, yeah, maybe also just a related thing, maybe that, yeah, what's the best way to say this? It's yes, maybe it's just yeah. Another maybe useful thing to keep in mind is, which is very similar to this, is kind of that sort of what's the right way to say this? So it's like normally when you play these like what on earth is the best way to say this? Again, the point is that it's say like, yeah, our like again, the character formula for a Verma, it was like this partition function thing. And the point is that like there's some standard picture where when you flip over the partition function, you almost get a modular form of weight 1/2, but you're off by this. I mean, this is exactly, actually, I think I'm just repeating what Ginsburg's suggestion was, which is basically that you actually need to multiply this q to the 1/24 to actually get a modular form. And that 24 up to some minor shifts is basically that 26. Yeah.
Thank you.
Yeah. Okay. Great.
Can I ask another question?
Sure. Yes.
Just so in the semi-simple case, we have like the parameter space for Verma modules is related to the center of the universal enveloping algebra. I believe in the Virasoro case, like the central action of the universal enveloping algebra.
Yes, got it. Using the block decomposition. Yeah. Yes.
Yes. So here, from all I remember, like the center is trivial, right?
Yes.
So is there like another interpretation of the space of parameters for Verma module?
Okay, so maybe the image is, so again, so the literal space of parameters is all just some Cartan. So, but maybe you mean the set of blocks.
Yeah. So.
Yeah. Yeah. So we'll so maybe the statement is basically, it's kind of that. Yeah. We'll see the answer in a second. So it's basically the same way that like sort of like literal parameters for Vermas is like T star. Parameters for blocks is you have to mod up by some finite Bowl group. So the basic picture is that it's like when you go to the W algebra, it's okay. It's informally speaking, it's like you're starting with, well, okay, there is such a picture, and we'll give it in a second. Yeah, it's a good question. Okay, maybe so. Actually, should we restart?
Thank you.
Of course.
1 minute.
1 minute. Okay, great. Yeah. Yeah. But yeah, actually, sorry. I mean, I should emphasize, Nikolai. So it's literally just some super explicit thing. Like there's some usual formula for what the Tate extension is of some graded Lie algebra. I mean, and you can literally just plug in Virasoro into that, and you just get 26 out. So I mean, there's not, I mean, basically, yeah. Sorry, it's connected to a lot of cool things, like very nice things in number theory, very nice things in physics, but it's also just kind of, it's like a calculation you can sit down and do. There's nothing particularly mysterious about it. Yep. Okay.
We can start now.
Okay. Yeah. Great. Let me see. So how much battery do I have on this? Okay, great. Yeah. So let me just move this over to where I'm sitting. Okay, great. So, yeah. So let me maybe sort of try to describe for you sort of, so how did these pictures we drew, how do they generalize to higher rank W algebras? And kind of, so it's, So okay, so let me sort of tell you sort of so the picture for Verma embeddings. So okay, actually, so first let me sort of say before I get to the general case. So like so first, what's the literal answer to this first question? So the whole point is basically that like what's the right way to say this? It's like the whole point is Virasoro is just some animal that just has its own great inner life, and you can just sort of study it directly. But the point is that then to see where these dihedral groups and whatever are coming from in just thinking about Virasoro just by itself, it's not clear. Like it's kind of mysterious. Like, say for example, the way that these embedding diagrams are first computed, it's like they really just took Virasoro as is and just played with like Shapovalov determinants and these types of things. It's really just kind of yeah. So the whole point is that it's kind of the answer is it comes from when you think about Virasoro as sort of the Drinfeld-Sokolov reduction of sort of affine SL2. The point is that just the Weil group for this creature, the Weil group for SL2 hat just is just an infinite dihedral group. So the basic idea is that sort of so if you look at SL2 hat Verma embeddings, you'll see the following types of pictures. So well, basically you see the same pictures. Let me just say it that way. So you see okay, and so so kind of and there, let me recall for you that that's kind of something you can kind of you can play with. You can see that kind of directly, kind of just use just SL2, simple SL2 games, and they kind of give you all these pictures. Okay, so so this suggests the following thing, which is kind of so let me recall for you. So there was some sort of functor of Drinfeld-Sokolov reduction that went from SL2 modules to Vir modules. And for example, like the standard example was when you took the vacuum algebra for SL2 at some level K, like you know, Virasoro was defined for you as the Drinfeld-Sokolov reduction of that guy. So, well, sorry, again, the W-algebras in general, they're presented to you in this way, and for SL2, you just get Virasoro out. So this is you get Vir at some central charge. And sort of here, I mean, by Vir, I mean the corresponding sort of the Virasoro vertex algebra, yeah. Okay, and so so then the picture is basically that so this was kind of for SL2, this was in basically in kind of this first paper of Feigin and Frenkel. This is like literally the unique one of these that I happen to remember the date for, sorry, but like they well, sort of, it was kind of the suggestion was that that this psi plus sort of when you restrict it to just category O for SL2 hat, that should map the category O for Virasoro. And the basic thing was basically that it will send Vermas to Vermas and simples to simples or zero and kind of with some sort of explicit criterion. And it's kind of exact. The exact. Okay. And so then in particular, so the rough statement is that kind of so then kind of so again, so on what's the best way to say this? So basically on this side, there's kind of there's manifestly sort of Kazhdan-Lustig type combinatorics. I mean, basically, you actually have a group in the game. You have the Weil group. You literally have the dihedral group just sitting in all the relevant representation theory or geometry or whatever. And so basically that's the thing that controls the character formulas over here. And then you have this t-exact functor, so it just kind of, it's that, and knowing it has these good properties then tells you that, so basically the point is that the character formulas on the right-hand side sort of follow from the character formulas on the left-hand side. And because that's where we get kind of the dihedral group. Okay. And so let me tell you how this adapts to the higher rank W algebras. So this was kind of then basically, so this was kind of then conjectured by Frenkel, Wakimoto, and proven by Arakawa that basically, so there's a similar picture. So there's some minor caveat which I'll actually, well, I mean, I'll just mention, but then we don't have to worry too much about it. So it's kind of okay. So it's now for just, so if you take a general higher rank affine Lie algebra, so not say for SL2, but for like, I don't know, SL10 or something. So you still have some sort of nice functor from the category O for just the affine Lie algebra itself, no funny business, going to the category O for the W algebra. And it still has all these nice properties, which is kind of its t-exact. It sends vermas to vermas, and simples to simples are 0. Okay, great. And so in particular, the point is that it's so then the upshot is that sort of category, you know, basically sort of W modules, or maybe say category O for W, is kind of controlled by just affine Baal group combinatorics. So basically, you know, concretely, it's kind of all the character formulas are just given to you in terms of, well, basically, the character formulas on this side are given to you in terms of, you know, affine cardinalistic polynomials, and so are the things on the other side. So with that said, so let me first give you an analogy, and then we'll slightly correct the analogy. Oh, sorry. So maybe before I do that, so there's some technical fine print here about sort of basically one of the key maybe insights in this kind of this work of, well, they do many things, but just say for this one particular part, kind of one of the key things they identified was that it's like the basic subtlety when you go from SL2 to a higher rank thing is that kind of this basically the functor that you would first try to use, which is just the usual BRST reduction, the one that literally spat out W when you plugged in Kac-Moody, it's not going to have these very nice sort of t-exactness properties when you plug in category O. So just in general, when you plug in like random modules, you don't expect any of these functors to be t-exact. But the statement is that it's, so this usual reduction happened to be t-exact for SL2 when you only worked with category O. And you have to slightly tweak the functor in general to kind of make it t-exact for higher rank groups. And sort of maybe for people who know these types of words, like it's related to this business of like when you talk about a Whittaker character of like a p-adic group or something, you can pick the conductor, right? You can kind of slide it up and down, and you basically you have to slide this character slightly. But anyways, it's some technical thing, but the upshot is just that in some very precise sense, like the category O for the W algebra is some sort of Serre quotient of the category O for G hat. And so in fact, so let me try to say that slightly more clearly. So maybe here's an analogy. Sort of, what's the best way to say this? Right. So recall that kind of just in category O, for a semi-simple Lie algebra. So when you go from, say, you have kind of regular blocks, and you kind of have, say, singular blocks. And kind of sort of the statement is that you normally have some sort of translation functor. And sort of the statement is that so T is kind of, it's T exact. It sends again Verma to Verma, and again simple to simple or zero. And so I mean, so in that sense, kind of all the combinatorics for the singular block is some sort of quotient of the combinatorics for the regular block. And sort of even more concretely, sort of if you know these types of things, it's sort of when you look at the Grothendieck groups, maybe the Grothendieck group on the left-hand side would just be something like the Weil group. And the Grothendieck group on the left-hand and the right-hand side, the first approximation is kind of looks like the Weil group modulo some parabolic subgroup. And that's related to kind of, well, if you wish, there's a way to talk about sort of parabolic or kind of casualistic polynomials. And so you can sort of directly say that for a singular block, everything's given in terms of parabolic casualistic polynomials. But it's kind of, again, you can just read them off of this. So so in the present case, and in fact, so maybe yeah. So kind of so for W, it's basically that same picture. So now it's so when you take a block for G hat, and you take this reduction functor to get a block for W, here's kind of the picture. So the funny thing is, what's the best way to say this? It's kind of, so basically this was, as far as I know, this picture of what's going on, I really hope I'm remembering their names correctly. It was found by sort of two physicists. It's De Vos and Van Driel. And it's kind of, it's the following very nice picture. So it's kind of, so the idea is that you should think of this as it's some sort of version of a translation functor. But with the following slight technical caveat. So the idea is that it's a block for G hat. Let's just think about what's going on. So on the Grothendieck group, this thing looks like already it's the affine Weil group modulo maybe some subgroup coming from the singularity of the block. And so the point is that what this looks like is so the rough idea is that it's kind of this we make, well, what am I trying to say? Like so just for the finite dimensional algebra, when you make this principal W algebra, that's kind of just the center. It's related to kind of, I guess, the question during the break, or comment during the break. So it's kind of, so there it's kind of passing from Verma modules to just their central characters, that's finite Weil group to 1. So there's kind of some collapsing of Weil group orbits. So it's the same picture here. Oh, okay, yeah. So the point is that now it's like, so to speak, it looks like a translation functor, but kind of it's on the other side maybe from what you would normally do in category O. So it's basically you're going from a one-sided quotient of the affine Weil group to a two-sided quotient. Okay. And by the way, so an important comment is that so for experts in this type of stuff. So you know that when you describe a block of category O, it's not really given by the whole affine vowel group normally. It's given by, you know this for semi-simple algebra too. It's normally given by some sort of integral vowel. And in general, really what you should be putting is that it's some integral vowel group. And the whole point now is that it's so because like the basic puzzle that you would run into is sort of like, so if we're supposed to be literally always passing from a regular block to a singular block, how on earth could we ever still get, sort of, so to speak, like, what am I trying to say? Is this how you do this? Yeah, there we go. Wait, so the point is, this looks like a regular block for SL2. This looks like a singular block for SL2. And kind of the point is like, roughly it's kind of, you're collapsing, I think it's every two of these down to one thing to get to just this picture. So the idea is that kind of, it's how on earth could you still get this picture after Drinfeld-Sokolov reduction? And the whole point is that it's related to kind of, like basically if you have an interesting block such that this intersection happens to still be trivial, then kind of if you have a nice regular block of that form for the affine Lie algebra, it can just survive and give you an isomorphic block for the W algebra. Okay. Anyway, so now let me maybe sort of say also kind of so sort of what's the, so this is kind of at the level of kind of sort of some of the combinatorics. And let me sort of try to slightly upgrade this for you, kind of for, how do you say this not as a statement about Grothendieck groups, but as a statement about the categories themselves. Okay. Yeah, so again, so the point is that, so remark is kind of, so in general, so the work of Frenkel, Katz, Wakimoto, and Arakawa tells you that sort of the character formulas for W are given by a kind of, like, the point is that it's kind of biparabolic affine Kazhdan listed polynomials. And again, the picture is, it's the two-sided is exactly these two sides. And again, the picture is exactly that one side comes from the singularity of the original block for Kac-Moody. The other side comes from you're doing this reduction to the W algebra. Okay. So now, so let me say what's the best way to say this? Yeah. So kind of so basically so let me recall for you so okay, so question. So for example, here's the type of thing that you would want to be able to say. So how can we make precise the feeling that, or the hunch that, not just say character formulas, but the entire block only depends on this kind of, this double quotient. So the whole point is basically, it's just like, just think about it just in the generality of, I just have some Coxeter group and I'm picking sort of two parabolic subgroups. So just, basically, i.e. just Coxeter combinatorics. Okay. So I mean, like, concretely, like the type of thing that you'd want to be able to say is that, like, sort of, if we go back to these embedding diagrams for Virasoro, like somehow, so strictly speaking, like you know, if I tell you that there's two blocks in which all the Verma embeddings kind of look exactly the same and they look like that, you know, it seems like unthinkable that these would not actually just be equivalent as categories, and probably they should even be sort of canonically equivalent in the appropriate sense. And so you want to articulate sort of, so the whole one is basically you want to say that this kind of, the combinatorics for Verma embeddings, we know that kind of it typically tells you what the combinatorics is for the character formulas, and then you normally want to say that that actually typically tells you sort of not just these numerical things, but the whole category itself. Okay. And so the statement is that sort of, so you kind of ask yourself the question sort of what's normally the type of category that would be associated to, like, you take your Weyl group and you mod out by parabolic subgroups on both sides. And so kind of, so maybe the statement is that kind of maybe the first, what's the best way to say this? Yeah, so maybe the more psychologically maybe easier one to think about first is kind of, so if you took something like let's say if you took sort of perverse sheaves on something, you know, whatever, the constructible derived category, let me not worry about these types of things. But sort of typically the normal statement is that it's sort of what these type of, maybe the simplest thing to say is that maybe sort of, if you take sort of, say, a flag variety modulo two parabolics, you know, a partial flag variety mod, G mod P mod Q, sort of the point is that the Bruhat decomposition here is literally that your group G is going to be the disjoint union of P W Qs for W in, now the whole point is that it's, you know, if it was just the Borel on both sides, you would literally run over the whole Weyl group, but sort of you're dealing with these bigger parabolics, so you need slightly less. Okay, so maybe what I'm trying to say is that, like, there's some sort of picture where it's sort of doing a double coset sort of by two Cox or subgroups. Typically that kind of looks like you're doing some sort of constructible sheaves on, like, your group modulo sort of two parabolics. And sort of the stabilizers or whatever on both sides are telling you which parabolics to pick. Okay. So the statement is that kind of this isn't literally the right picture for what we're doing. I mean, well, it kind of is, but it's not quite. So in fact, so this is almost what one would want. But not quite. And in sort of the reason why it's not quite what one wants is kind of it's not anything complicated, which is just that sort of, say, in this normal picture, when you start with, say, like G mod B mod B, and you go to, say, like G mod B mod P, this doesn't, so this, yeah, I mean, this does not send simples to simples or zero. Yeah, so kind of yeah, I mean, yeah. So I mean, the simplest thing is kind of like, suppose the P was the whole group, then you're talking about taking global sections of your IC sheaves, and you know, you have yeah, this, I mean, global sections is a great functor, like, it just doesn't destroy anything. So yeah, so instead, so maybe, well, let me sort of remind you sort of the maybe the whole point is that it's, so when you look at a double coset like this, and you look at sort of this, the sort of maybe just the formal, you know, formal linear combinations of these things, a priori, there's two types of things this could be, which is you could literally take the Weyl group, and somehow you're sort of killing these two parabolic subgroups on the left and the right. And sort of the point is that it's so the whole point is that kind of typically, I mean, say if you're in the simply laced case, you have two choices of what character to actually put there. Yeah. And the point is that it's when you pick sort of in the appropriate normalization, when you pick the trivial character, that's what's giving you this geometry. But instead you can pick the sign character, and that gives you a different geometry. Okay. So instead, kind of basically we want to work instead of we go from trivial characters to sign characters. And so the point is that it's what the relevant category is, it's kind of, we want kind of the causal dual category of perverse sheaves. And the point is, I mean, why do we want this causal dual one? It's literally just all these numerical things that we saw happen. And these things about simples going to simples or zero, the kind of translation functors, those are something about not averaging to a parabolic, but instead averaging with respect to a Whittaker character. And you know, we're generally kind of, the W-algebra was made from some sort of, it was some game with a unipotent subgroup and a character, not a parabolic. So the upshot is that, so there's something you can, so actually let me first say it in maybe first this case, because it's maybe slightly easier to say. So the idea is that it's, so now if I pick, okay, so there's some word to say, but let me just, okay. So the idea is that, okay, so there's actually, I guess, so Jiwei will explain this all very nicely, and Professor Ginsburg will explain this all very nicely too, if you ask him. Kind of the picture is kind of the causal dual operation to averaging from like a Borel to a parabolic is you do some Whittaker averaging where you go from like the Borel, which you think of it as like basically n equivariant objects up to some technical details, to kind of you go to n equivariant objects, you have to pick a slightly different n, but some technical detail, but now you turn on a character. Okay. And like the more non-trivial the character is, the fewer objects you'll have. And in that sense, it kind of behaves like numerically like passing to equivariance for a larger subgroup. It's kind of it's a harder condition to satisfy. Okay, so right. So the literal statement is the type of categories we want is basically it's you do the following things. It's you take so let me give you a concrete definition of it, and then let me give you a slightly less concrete thing that's maybe more conceptually helpful. So so you can talk about what's the best way to say this? Yeah, so it's so the thing is that when you take the category O, say a block of category O for the W algebra, what that'll be equivalent to is you do the following thing. So it's so it's going to be perverse sheaves on, okay, there's some, okay, there's going to be some group associated to your block, with the integral vowel group of your block, and then you kind of let me sort of sorry, this is like horrible notation. Sorry. So the point is that so morally it's you're doing some sort of category of Whittaker sheaves, but now kind of you put a Whittaker condition on both sides. Okay. And sort of so here kind of so maybe a nice way to say what this thing is in fact, let me just sort of say it for the whole category of sheaves. Is you can just take sort of the usual Hecke category. So again, we're trying to talk about passing to this two-sided quotient. And the point is that it's at the level of growth groups, you can phrase it as you start with just the original growth group and you tensor by two characters on two different sides. And so here's how you say it. And I mean, basically you're allowed to say the exact same formula. In fact, so let me just write it like this. So basically, you have these two Levy subgroups. LP. And then we have, oh, sorry, that was kind of Q in the previous notation, sorry. Okay, and so concretely, you're doing Whittaker averaging from just the usual Hecke category to kind of Whittaker things, but you're doing the Whittaker averaging on both sides. And that's the funny additional thing you get for W algebras that you don't see for just the Kac-Moody algebra itself. So now it's kind of but here's this is some non-degenerate character LP. Well, or N. And then you do a similar quotient on the other side. Okay, so right, so anyway, so this is the type of category that would have this kind of the type of casualistic combinatorics that we saw, or that sort of Frenkel, Katz, and Wakimoto and Arakawa saw. And so then the last thing to explain maybe is how does one again, so how do you actually sort of justify that that's all that's going on? Okay. So again, so maybe let me emphasize that. So literally all we're saying is the following thing. We had the following picture of the Grothendieck group, which is you take some sort of integral vowel group. So this is some sort of parabolic, or sorry, it's some subgroup of the affine vowel group, which is also naturally a Coxeter group in its own right. And like what we needed to do was we needed to tensor it on sort of two sides by a sign character. So sign character 1 came from the fact that we were dealing with potentially a singular block. So it's kind of the stabilizer of maybe lambda in T star itself. Oh, and in fact, yeah, sorry, well, yeah. And then the other quotient was we also turn on some sign character, and that's kind of this Whittaker quotient. This is the Drinfield's local production step. And what you have to do is you take W lambda intersected with the finite vowel group, sort of viewed both as subgroups of the affine vowel. And that's this picture, okay? And sort of the point is that it's so there's some obvious quotient functor from not functor. There's a quotient map from just if you didn't have this quotient, oops. Because if you only had a one-sided thing, yeah, so basically the one-sided thing, this would look like this is a block of category O for G hat. And the point is that this is a block for W. And this kind of the obvious thing where you just impose that sign, you take the sign quotient, the sign projector on the left as well. That's this functor of Drinfield's local reduction. Okay. And it corresponds to just averaging of sheaves up here. Okay, so maybe before I explain how you actually justify these types of equivalences between the blocks of category O for W and these types of by Whittaker categories, are there, I feel like there probably should be questions. Well, I don't know.
What's the difference between psi plus and psi minus?
Yeah, okay, excellent question. So it's literally the following thing. So sort of Uh, yeah, so, okay, so let me maybe just sort of say it for you in, yeah, okay, so basically, so, yeah, in fact, so it's not anything complicated. Um, so these are kind of, let me just tell you, yeah, they're both Drinfeld-Sokolov reduction against some sort of character of n double brackets t. And just let me tell you what those characters are. Okay. So basically the point is that so psi plus, I mean, so again, the point is that if you're actually doing something like completely canonical or whatever, there's some sort of one form twists and whatever everywhere. In fact, yeah, I mean that's kind of related. Well, actually, well, sorry. So the point is that so psi plus is kind of supported on. Let me just say it incredibly informally. Just n tensor tensor with dt over t. And kind of there, it's kind of just maybe, it's you send all your simple root vectors that, it's kind of, so it just like when you restrict it to this, say, vector subspace, it looks like just, so basically it's kind of, you send like EI tensored with dt over t to 1, for I and I, kind of your simple generators. And the point is, so psi minus, so maybe first, let me try to motivate it to explain like what on earth is going on. So it comes from exactly this type of picture. So it's like, so like normally when you're doing an averaging functor from equivariance for a Borel to equivariance for like some other unipotent subgroup with a character, like the condition you want is basically that like the Borel and the unipotent are appropriately transverse. Like they form some big cell somewhere. Okay. And so the idea is that like the whole point is that it's this sorry, so the picture is that it's kind of like if you just have, say, like inside just G of O, like the picture is kind of, so there's a standard way you can make something transverse, which is say like if this is B and this is n minus, and say this is like the first congruence. So we're starting with literally just a big cell in the finite dimensional group. Yeah. So the point is that it's kind of, so basically it's the type of functor which looks nice and transverse is going from Iwahori equivariance. So that's kind of the preimage of B under the evaluation map. If you average the kind of, so this is kind of maybe evaluation inverse of B, and this is evaluation inverse of n minus. Yeah, so if you do some sort of averaging functor from I invariance to like this I minus psi invariance, that's going to have very nice properties. Basically, it's just you have that sort of transversality where you want it. So the basic point is that, but the whole point is that it's like if you just stare at what you've done, now the relevant Whittaker character, it's not attached to the things multiplied by T inverse, it's attached to things multiplied by just 1. Okay, so there's kind of that shift in which slice the character is supported on. It's not on dt over t, it's just a dt. Okay? So the point is that, that's, so this kind of psi minus instead, that's going to be supported on basically just n tensor 1 or n tensor dt or something. Okay? Yeah, great. And maybe just the statement for kind of you to think about yourself, if you'd like to, is that sort of why doesn't this really cause problems if you're just talking about SL2? And the point is that for SL2, you get lucky, and these two different choices, in the appropriate sense, they differ by just like the Dynkin diagram automorphism of SL2 has. So you kind of all the exactness and transversality stuff you would want that you see for psi minus, you also see it for psi plus. But that doesn't happen for higher rank groups. And it's not a big deal too either. I mean, you just work with some category O for some funny conjugate of the usual Iwahori, and then everything will work fine. So it's kind of, yeah, not so important. Okay, yeah. Are there other questions? Okay, so then maybe in the remaining time, let me try to say a few words about what's going on with this type of equivalence. Because again, the point is like this is the type of thing which would store all the types of character formulas you want. Kind of, and in particular, but by the way, the type of funny thing this implies is that it's kind of, when you take blocks of category O for the W algebra, they have these sort of nice graded versions, and they're kind of causal dual to sort of these kind of bi-parabolic categories. Where do we see them? Yeah, like these types of things. So yeah, in fact, basically, there's a funny thing actually, which is that it's, so if you look at the paper of Bezirkovnikov and Yoon, they prove a bunch of causal duality equivalences. And just sort of, if you want the W algebra to fit into those things, if you just literally stare at what they wrote, they didn't write what happens when you put parabolics on both sides that are both strictly greater than the Burrell. But anyways, it's exactly related to, I mean, this stuff is literally the answer to that question. Anyways, the point is just that, I mean, there's some fun things here. Okay, so let's kind of finally justify. So let me sort of explain the localization. Oh, kind of very small again. So the idea is that it's kind of so this is kind of with Raskin. I mean, it's in some sense not. Well, okay, what am I trying to say? So okay, so what's the basic idea? Well, in some sense, it's that right. So what, like, where do you normally localize? So the whole point is this: it's like we can really just think about W representations as just certain G hat representations. Okay, that's what this whole affine Whittaker model business or whatever is, right? So I'm saying that sort of, so we know, thanks to Sam's very nice theorem, it's kind of a version of Scriabin equivalence, so that kind of W modules, you can think of them as just Kac-Moody modules, which are kind of Whittaker equivariant. Okay. And then the idea is that kind of, so Kac-Moody modules, you know, you typically relate them via localization theory to something like some sort of D modules on sort of affine Flag varieties or something, right? And of course, you know, there's levels and there's twisted D modules and whatever. I mean, there's all the usual, you know, all the usual sort of modifications. So, you know, normally you relate sort of, typically the more, so the whole, again, so this is actually related to a question earlier. So let's recall it. For a finite dimensional Lie algebra, you can literally say like, okay, well, if you take literally D modules in a Flag variety, they'll give you Lie algebra representations at a fixed central character. And the funny thing is, right, so in the affine case, you're not quite allowed to say that anymore, but you still can say you have these fully faithful embeddings and whatever. So, but anyway, so the upshot is that, so then what we'd expect is that, so the things which should be related are, if I take now these Whittaker equivariant things, these should just be related to then just Whittaker equivariant D modules, right? That's kind of what always happens under localization. Okay, and so the statement is that in the appropriate sense, this so you can literally just say this, provided you've set up the localization theorem to begin with in the appropriate technical framework. So namely, so what do I mean? So it's kind of so yeah. Yeah, if I can maybe actually let me just actually write this down. So okay, so that's why I say this. So well, okay, sorry. So yeah, so maybe I guess I should probably call this a theorem or something. So okay, so maybe here's a theorem. So basically, so okay, so let me break into two cases. So okay, so there's some technical fine print. I mean, but it's the usual fine print in all these stories, which is in fact, sorry. So actually, let me sort of say so yeah. So the basic thing I'm trying to say is the following thing. So it's ideally you want your localization terms to kind of be actually well adapted to the T structures on the categories you're considering. And the basic dichotomy we saw here is that kind of sort of for one range of central charges, you get pictures which look like there's like a minimal stratum and then just higher strata. And sort of for the complementary range of central charges, it kind of looks like there's some sort of big cell and then sort of a bunch of strata on the boundary of it. Okay. And so let me recall, basically, because things are infinite dimensional, like roughly, you can't ever get from like the smallest stratum to the big cell. Like those kind of will live on different fragments. So there's some standard ways to say this. So there's kind of, so let me try to say this sort of so in fact, let me just sort of say for regular blocks, there's statements for singular blocks too. Yeah. So it's say for, let's say a negative level. So there's kind of there's a T-exact functor, which is if I take sort of say Whittaker sheaves on the affine flag variety, sort of twisted by my level, there's just some global sections functor which turns those into W modules at sort of that same level. And kind of sort of for so there's some fine print about sort of, I mean, there's some for almost all K and lambda. Anyway, there's something super explicit about just singularities of, what walls you lie on or whatever. You get sort of, it's kind of, this is maybe it's the embedding of a direct sum of blocks. And by the way, sort of a feature of this I want to emphasize is that you guys talked about this adolescent Whittaker stuff last week. And so you can also think about this literally as just Iwahori Whittaker sheaves. Great. And then for K positive, there's a similar statement, which is now kind of, you have to be slightly careful, but it's kind of, so let me, yeah, in fact, maybe here's a safe way to say it. So when I say it like this, it'll actually be kind of, there's no fine print. So, okay, so there's like, there's some standard game where sort of, if you want pictures with a big cell, the point is when you take BunG on P1, that has a big cell, right? You have the trivial bundle that's open. And sort of there's some flag variety version of that as well, where now you kind of, you put a B reduction at one point as well. But anyway, so this is kind of BunG P1 plus B reduction at this one point. Yeah, so we still have this global sections functor. And again, this kind of, it's T exact embedding of a direct sum of blocks. Great. And so I should say, so the upshot is that the categories on the left-hand side, they have exactly the type of combinatorial, you literally have some Schubert stratification, those correspond to the Verma modules, the streak extensions correspond to Vermas, intermediate extensions correspond to simples. The character formulas kind of, they're given by cardinalistic combinatorics basically on the nose. And sort of in some sense, that's kind of, this is the, well, I mean, so I guess, yeah, you can sort of formally deduce from this stuff some of the things that we wrote earlier, which was kind of these types of sort of, endoscopic type descriptions, or integral vowel group type descriptions of the blocks themselves and all of that. Basically, because sort of for Hecke categories with twists, one has all those types of descriptions. It's kind of due to Lustig and Ian. Okay, yeah. So maybe let me also maybe say one last comment, because this sort of sometimes people ask about it. So there's also some very beautiful picture of like, yeah. So we described, say, for the trivial module, how you resolve it by Verma modules. And for people who know these types of things, there's also some sort of there's these cool pictures where kind of you can also instead you can give like a one-sided resolution by Verma modules, a resolution going the other way in terms of dual Verma modules, or this kind of intermediate thing, which is some sort of two-sided resolution by Wakimoto modules. And those things also do have a nice interpretation, basically going back to Feigin and Frenkel, where it's the target for the localization theorem is no longer going to be T exact, but now you deal with Whittaker sheaves on the semi-infinite flag manifold. You can all do that. It's not, as far as I know, this is not written anywhere, but you can do that, and you can still talk about some derived equivalence between a bunch of blocks of category over the W algebra and Whittaker sheaves and semi-infinite flags. And this will have the property that basically like, well, basically that kind of these Wakimoto type or free field modules for W algebras, they also fit nicely into kind of the geometric picture. It's kind of understood how that works. Okay. Yeah, so maybe let me just make a couple final comments and then we can kind of wrap up. Yes.
Oh. Gurbir, are you still here?
Yes, hi. Yes, I am. Sorry. I somehow got kicked, but then I'm back. Yeah. So can you hear me?
Yes, thank you.
Okay, yeah, sorry. So yeah. So the same is basically there's similar pictures and formulas for sort of every nilpotent orbit. and sort of there's kind of well, it gets well. I mean, there's genuine further complications that are actually extremely interesting, and they have a lot to do with sort of Springer theory and all that kind of stuff. But it's kind of so maybe the statement is kind of the funny thing is basically the way to think about it is that like sort of like in some sense like there's the confusing thing is that when you meet these kind of principal W algebras, yeah, it's like a lot of what this seminar has focused on, and for good reason, is that like basically because those things satisfy Feigin-Frenkel duality, like they're easy to directly use to kind of get results in geometric languages. But the statement is that kind of sort of these for W algebras associated to other nilpotents, there are subtler but extremely, I mean, basically those things sometimes in good situations have to do with sort of equivalences in like relative Langlands or whatever. But the basic upshot is that like there are entirely similar pictures, but just basically it's kind of because like morally the W algebra shows up because like you pass from some stack quotient to some invariant theory quotient. It's always easier to deal with invariant theory quotients, and like invariant theory quotients, say for like your G mod G and G check mod G check, like those stacks are different, but the invariant theory quotients are the same. And so maybe this is to say that just kind of it's everything that we said in this talk today, kind of it doesn't really like you can use it combined with Feigin-Frenkel duality to do interesting things in geometric Langlands, but like these results themselves, like I mean, basically there's only one group mentioned the whole time, and so like they're kind of agnostic with the fact you're really working with the principal W algebra. Yeah, okay, so maybe I'll stop here. Yeah, thanks.
Thank you.
Yeah, I guess are there questions?
Yeah, there's a question. You mentioned something about the non-principal case, there being some equivalences related to relative Langlands. Is this like documented, or just curious what you were thinking of?
Is this what?
Is this documented anywhere, or I'm just curious what you're thinking of in particular?
I think the good news is how to say it? Well, so the short answer is basically so what on earth am I trying to say? Like well, I guess it's so basically there's like I mean it's around this stuff kind of that goes under the name Gallardo conjecture. So it's kind of well
Sorry, what conjecture?
Oh, sorry, Gallardo conjecture. Sorry, so let me just say it properly. The point is just that like the whole point is that it's kind of for some, let me say it like horribly, but hopefully sort of right. So it's like sorry, so the literal answer to your question is like yes. So like for at least for certain nilpotent orbits, like say like basically like think like instead of so principal case is like one big column, and say like think like hook type. So kind of just basically the rough point is that it's people know at least sort of conjecturally what the dual of those types of generalized Whittaker things are under local geometric Langlands. And yeah, so well, okay, the relevant statement is that so there's a bunch of extremely cool conjectures kind of I guess introduced in physics by Witten and Gallardo and Mikhailov, and then kind of Braverman, Ginsburg, Travkin, Finkelberg, and Rotel Yang have they have lots of very nice results about this. So it's like there's those types of equivalences, and you combine and kind of there's also equivalences kind of coming from the same pictures, which are kind of these called like trialities for W algebras. So this is something that like people like Kreutzig and Andy Linshaw and Nakatsuka. Like, there's generalizations of Feigin-Frenkel duality for other classes of W algebras, and basically kind of those types of things have to do with relative, matching, taking columns between things and matching them for basically boundary conditions coming from relative Langlands. Or, kind of the nice boundary conditions you study in relative Langlands, they imply a bunch of things like Feigin-Frenkel duality for other W-algebras. And you can match these kind of perverse sheaf descriptions, and that's kind of the relevant phrase is Gyoto conjecture. Yeah.
Awesome, thanks. I'll ask you more about it later.
Yeah, sure, absolutely. This is great. Yeah. Okay, cool. Yeah. Are there other questions?
Yeah, one more question.
Yes.
The Whittaker category, how does it show up in this embedding localization theorem?
Oh, sorry. Give me 1 second. Oops.
Whittaker category show up in the embedding?
How does the the by Whittaker category? Is that what you asked?
Yes.
Yeah, sorry. So okay, so the statement was that I literally just kind of I was slightly lazy. So it's sorry, when you genuinely deal with singular blocks, you're not localizing on affine flags anymore, but you're doing really like you're already putting some Whittaker condition. It's basically instead of modding up by Iwahori, you're modding up by some Iwahori Whittaker condition already. So then now you get kind of some sort of Iwahori Whittaker condition on both sides, and that's this by Whittaker, this kind of two-sided quotient picture. Sorry, because basically, I only wrote the localization theorem for regular blocks above. That's the only reason.
For example, the bi-Whittaker category acts on the Whittaker category on the left. Do you see this action?
Yeah. That's basically affine Harish-Chandra bimodules. Well, I mean, it depends on what side you're acting on. Yeah. Yeah. So, in fact, yeah. Sorry. So, in fact, sorry, guys, I gotta run. But yeah, if you have more questions, you can email me and I can try to answer them or whatever. So, yeah, thanks very much. Yeah, it's good. Okay, great. Bye.
All right. I think what happens, like, for example, in the finite dimensional case, this kind of localization, like